Today we're going to look at limit of function sine x when x goes to infinity. We need to argue that it does not exist. When you look at this problem at the pre-calculus level, that it is with trig and pre-cal BC class. So for that, we use intuition. That is, we notice that sine x is a periodic function. That is, as getting bigger and bigger, it keeps this pattern. That is, periodic function with period of 2 pi, right? So when n goes to positive infinity here, you're going to have this periodic function oscillating from -1 to 1. So intuitively, we argue that the limit does not exist because it does not converge to a constant value L, right? Now, how to do this in a more rigorous way if you are at the calculus or at the college mathematics level, right? Now, we need to come back to the definition of the limit. Now, here's the limit. When we say a function has a limit when x goes to infinity, this is what it means. It means for any epsilon greater than 0, there exists some m, maybe some big number, such that when x is greater than m, we're going to have the value of the function here is going to be bounded by epsilon, no matter how small the epsilon is. All right. So if that is the case, then we say the function has a limit L. Right. So here we know that that's the mathematical definition, and we want to argue that sine x, the limit, does not exist. So how do we do that? So we're going to show two different methods. One with the definition, the other with an important property. When you take calculus class, you probably learn what is called the sequential criteria for the limits at infinity. We say that if a function is well defined for some interval, up to the positive infinity, we say that if there exists a limit here, L, then it says this condition is true if and only if any sequence, I pick a sequence an such that if this sequence value goes to infinity as n goes to infinity, then we have the function of the sequence, those elements, is going to converge to the same value L. Okay, this L has to be the same. All right. So how do we use this theorem to prove that sine x, the limit, does not exist? What we can do is that assume it exists, and using this property, we're going to derive some contradiction. All right, let's go. So assume the limit exists and the value is L by the earlier property, the sequential criteria here. So what we do is we're going to define a sequence, 2n pi, right? And this sequence indeed satisfies the property that when n goes to positive infinity, the value an is also positive infinity. All right, so this is true. Now we say that from the theorem we know that the limit, the function f of fn is going to be L, right? And for 2n pi, of course, no matter how n is integer, of course, no matter how big it is always 0. So L must be 0. That's what we have. Now, if, however, you consider a different sequence, for example, 2n pi plus pi over 2, now this sequence also satisfies the criteria that when n goes to infinity, an indeed goes to infinity. So by applying the same theorem, we're going to get this L is going to be equal to 1. Earlier it said L equals 0. So that's a contradiction. We found two sequences satisfy the same criteria, and the limit of function with this sequence goes to the limit L. But L does not exist in this case because we have contradiction, L equal to 0 and L equal to 1. So a contradiction, which means the limit does not exist. All right, so that's one method proving in a more rigorous way that the limit of sine x at infinity does not exist. Now, can we use definition to prove it? In order to prove by contradiction with condition, you're going to assume the L exists, and the contradiction would be the converse of that, right? So it says for all epsilon greater than 0, if you can find there exists some epsilon, and here it said there exists m, so that as long as x greater than m, you can say, okay, maybe for all m, no matter how big it is, we can always find some x greater than m, but this condition does not hold. Then we have a contradiction. Okay, this is a very important practice. You're going to use it again and again in the assignment if you do the college level calculus class. All right, so let's try that. So here, assume the sine x, the limit at infinity exists, and it is L. Okay, we want to derive a contradiction. So we're going to pick some epsilon. All right, so we're going to pick epsilon equals absolute value of L, because L could be positive, could be negative, right? What we need to do is to find a contradiction by arguing that no matter how big m is, for all m greater than 0, we can find some x greater than m, but this condition is not true, right? So what is this condition here? This condition is true, then L, we're going to pick the epsilon here, right? So this is the when you change this absolute value, you're going to have this, right? Now, absolute value is not easy to work with, so maybe to make the algebra easier, first assume L is greater than 0. Later, you can argue the same thing if L is negative value, right? So assume L is greater or equal to 0. So this, we get rid of the absolute value here. Now we're going to rewrite this. We say that this criteria is equivalent to fx has to be greater than 0. Now we can find a contradiction easily because we know that sine x could be negative, right? And no matter how big m is, right? So let's go. So the argument is that no matter for all m, right? No matter how big it is, we can always find there exists some n big enough so that x is greater than m, right? Greater than this satisfied, but the function here is negative, which contradicts with this criteria. In other words, let's recap, right? So what we're saying that this is the theorem, but we have argued that assume the limit exists and assume it's greater than 0. We pick this particular epsilon. We argue that for all m, no matter how big m is, you can always find x greater than m with the property that this is -1, and argue that and this one would be greater or equal to epsilon and contradict with this definition, right? What if L smaller than 0? You can make a similar argument. The algebra is a little bit different, and the particular x value is also going to be different, but we're going to leave that as exercise. Please try it out if L is smaller than 0. So with that, and you derive a contradiction, which means we argue that the limit does not exist by using the definition of the limit. All right, so that's a very important exercise. Please do that offline. Now we have used multiple methods in argue that sine x does not have a limit when x goes to infinity. Okay? Hope you like the video. Please share and subscribe to the channel.